this video, we'll be solving paper 2 variant 1, October-November 2024, AS level chemistry. Question 1. Cobalt, rhodium and iridium are metals in the same group of the periodic table. The shorthand electronic configuration of cobalt is that of argon followed by 3d7 4s2. Identify what's meant by the argon symbol. So argon is a group 8 element. That has an atomic number of 18. When writing the electronic configuration, remember that each shell has subshells. So shell number 1 has subshell S, shell 2 has subshell S and P, shell 3 has subshells S, P, D, and shell 4 has subshells S, P, D and F, where the number of orbitals in each shell is different. So subshell S has 1 orbital and each orbital can carry 2 electrons with opposite spin. Subshell P has 3 orbitals, and since each orbital can carry 2 electrons, that means subshell P can carry a total of 6 electrons. Subshell D has 5 orbitals that carry 10 electrons in total. Subshell F has 7 orbitals that carry 14 electrons. So the way that we fill up these orbitals, or the way that we write electronic configuration, is the lowest energy subshells are filled first, meaning the subshells that are closer to nucleus are filled before those that are further away from the nucleus, with a few exceptions. For example, 3d orbital is filled before 4s orbital. For the element argon that has 18 electrons, you start by filling it from the first shell, or 1s, that carries 2 electrons. Then you move on to the second energy level, starting with the lower energy subshell, that is 2s2, followed by the next energy orbital, which is 2p6. That's a total of 10 electrons. Then you'll continue this by moving on to shell 3 that has s, p and d orbitals. Now you're left with 8 electrons that are filled by 3s2 and 3p6 orbitals. This is the electronic configuration of argon. The lowest energy electrons in cobalt are in the 1s orbital. Draw the shape of a 1s orbital. That will be a spherical shape. Part 3. Deduce the number of unpaired electrons in a cobalt atom. As you can see, all the orbitals except the 3d orbital are filled to their maximum capacity in cobalt. All of these orbitals and 4s orbital are filled to their maximum capacity except for 3d orbital. Remember, subshell D has 5 orbitals that can carry a total of 10 electrons with opposite spin pair. Now 3d7 means first all of the empty orbitals are filled by 5 electrons. The 2 remaining electrons will pair up, and so that leaves you with 3 unpaired orbitals. Unpaired electrons. B. Table 1.1 gives some details of the stable naturally occurring isotopes of rhodium and iridium, and you're supposed to complete this table. The number of protons is equal to the atomic number. So there will be 45, 77 and 77. The number of neutrons is the mass number minus the atomic number. So that's 199 minus 77, which is 114, and 193 minus 77, that will be 116 for the two isotopes. As for the number of electron shells, the number of electron shells can be reduced by looking at the period in which the element lies inside the periodic table. Rhodium lies in period 5, so it's going to have 5 electron shells. Table 1.2 shows the relative abundances of isotopes in a sample of an alloy containing rhodium and iridium only. Define relative isotopic mass. This is the mass of an isotope on a scale where each carbon atom has a mass of exactly 12 units. Part 2. Use table 1.2 to calculate the relative atomic mass of iridium in the alloy. Give your answer to 2 decimal places. In this alloy you have 3 isotopes, but to calculate this answer you only want to find the relative atomic mass of iridium and not rhodium. If we were to calculate the mass of this alloy considering all of the isotopes, we would have used the calculation where the relative atomic mass of the alloy would have been, where the mass of the alloy would have been equal to the sum of products of the isotopic mass and the abundance of that particular isotope in the alloy, and you divide that by 100 because that's the total composition, made by all of the isotopes. But now the denominator is not going to be 100 and we are not going to add up the product of all of the isotopes. We will exclude rhodium to find the answer over here. So our calculation would only include the isotopes of iridium. That means the relative atomic mass here would be equal to 192.96 multiplied by 34.82. That's mass of one isotope multiplied by its abundance. In this alloy, and okay, let me just write it this way, I'll have more space. To that you will add the product of mass of the second isotope and its percentage abundance and divide that by the total abundance that is made up by only iridium isotopes. So you add these up, that's equal to 50, and the final answer is equal to 192.35. Remember to give your answer to 2 decimal places. Dehydrated rhodium chloride catalyzes the conversion of ethene to butene. Both stereoisomers of butene are formed in this reaction. We'll come to the stereoisomers part in a bit. Dehydrated rhodium chloride contains 20.5% by mass of water of crystallization. Deduce the integer value of X in the hydrated solid. Show your working. So the question is telling us 25% of the mass of this hydrated salt is due to water, and in order to find out the value of X in hydrated salt, we'll use the percentage by mass of water of crystallization. And for the first step, we'll find the MR of anhydrous rhodium chloride. So that's the mass of rhodium, 102.9, plus the mass of all of the chlorine atoms in this compound, which is a total of 209.4. Then we'll find the mass due to X H2O water molecules. Mass of one water molecule is 18. Therefore, mass due to X water molecules will be 18 multiplied by X. So now the total mass of a hydrated salt or RHCl3.XH2O is equal to 209.4 plus 18x. Okay, I'll clear this up here. Right, so now we know the total mass of the hydrated salt, and the percentage of water in this salt is 20.5. The percentage of water can be calculated by dividing the mass of water in this salt, in the hydrated salt, divided by total mass of the hydrated salt multiplied by 100. So that means 20.5 is equal to 18x divided by 18x plus 209.4 multiplied by 100. You divide both sides by 100 and are left with 0.205 is equal to 18x over 18x plus 209.4. You solve for x, so you'll shift the denominator here to the left hand side, multiply the bracket with 0.205, and so you're left with 42.927 plus 3.69x is equal to 18. You shift this 3.69 to the right hand side, subtract from 18. That means x is equal to 42.927 divided by 14.31, which leaves you with 2.99979, which will be rounded off to 3, the whole number 3. Part 2 defines stereoisomerism. Stereoisomers are molecules with the same structural formula and molecular formula, but they have different 3D arrangement of atoms in space. Part 3, explain how the conversion of ethene to butene can be described as an addition reaction. So ethene is a 2-carbon compound that is converted to butene, which has 4 carbon atoms. During an addition reaction, one molecule combines with another to form a larger molecule with no other products. For example, the examples that can be used from our syllabus include hydrogenation reaction, hydration reaction, and halogenation of alkenes. And this is a similar reaction where only one single product is made. Part 4, draw the 2 stereoisomers of butene. Okay, let's come to stereoisomers now. There are 2 types of stereoisomers. You will have geometric or optical stereoisomers. Geometric isomerism occurs due to carbon-carbon double bond when both of these carbon atoms involved in the carbon-carbon double bond are bonded to 2 different groups of atoms. Whereas optical isomerism occurs when a carbon atom is single bonded to 4 different atoms or groups of atoms. Since butene has a carbon-carbon double bond, that means it could form geometric isomers. Clearly butene does not have optical isomers, since there is no chiral carbon atom in this compound. There is no single carbon atom that is single bonded to 4 different atoms or groups of atoms. Okay, so it is going to form cis trans or geometric isomers with cis or trans configuration. In the cis configuration, both of the methyl groups will be pointed or projected in the same direction, and same can be said for hydrogen atoms. In skeletal formula, this is how you can sketch the structure. In the trans configuration, the methyl groups will be projected away from each other, and here is how you can sketch the skeletal formula for the trans isomer. Question 2. Chlorine is one of the elements in group 17 of the periodic table. A part 1. Describe the colors of group 7 elements. Chlorine to iodine at room temperature. Chlorine is yellow green. Bromine is orange brown. As iodine is black or silver gray. These are some properties that you will need to memorize: periodic trends, as well as some physical and chemical properties. Part 2. Describe the relative reactivity of elements chlorine to iodine as oxidizing agent. The strength of halogens as oxidizing agents decreases from chlorine to iodine, and to understand the reason, we need to look at their electronic configuration. In order for the halogens to oxidize another species, the halogen atoms need the nucleus of the halogen atoms needs to remove an electron from the other species using electrostatic force of attraction. So let's say if chlorine when chlorine oxidizes sodium, the nucleus of chlorine or the positive charge in chlorine will attract the outer shell electrons of sodium of the sodium atom, and going from chlorine to iodine or going down the group, the number of shells of the atom increases. This will reduce the nuclear attraction that is required to remove an electron from another atom. So as you go down the group, the size of the atom increases from chlorine to bromine. This will increase the distance that is found between the nucleus of a halogen and the outer shell electron of the reducing agent, which is sodium in this case of example. That means it becomes harder and harder for the nucleus of the halogen to attract this negative electron towards itself, and that is why it becomes harder for the halogens to oxidize in other species going down the group. So their oxidizing strength decreases. Part 3. State what's observed when chlorine reacts with hydrogen. The green color that's caused by chlorine in its natural state at room temperature will disappear because chlorine is now converted to hydrogen chloride. Explain why the thermal stability of hydrogen halides decreases down the group. What does thermal stability mean? To answer this question, we need to understand the meaning of thermal stability of hydrogen halides. The thermal stability of hydrogen halides depends on the amount of energy or the temperature that's required to break the bond between a hydrogen and a halide atom. The more energy that's required to break this bond, the higher the thermal stability of the hydrogen halide will be. Now this depends on a few factors, and going down the group, what happens is, again, the atomic radius of halides will increase, which increases the distance of the nuclei and the outer shell electrons of hydrogen and halide atom in the orbital overlap. Let me try to draw a demonstration over here. So let's say you have the hydrogen and halide atom that are going to overlap and have the electrons in this overlap for the covalent bond. You have the nuclei as well, which are the reason. The attraction from the nuclei are the reason. Attraction for them from the nuclei for the electrons in the overlap is the reason for this bond to exist. As the atomic radius of halogens increases down the group, that means this distance from the nuclei to the electrons in the overlap will increase. And as this distance between nuclei and orbital and electrons in the overlap increases, the hydrogen halide bond becomes weaker. This means that the hydrogen iodine bond is weaker than the hydrogen chloride bond, is weaker than the bond between hydrogen and chlorine atoms. Therefore, the hydrogen and iodine bond can be broken at a lower temperature due to its lower thermal stability. The halogenoalkane chloroethane forms when chlorine reacts with ethane by a free radical substitution mechanism. Define free radical. This is a species with one or more unpaired electrons, and due to this fact, free radicals are very unstable. State the condition for chlorine to react with ethane at room temperature. That would be ultraviolet light or ultraviolet radiation. Part 3, write 2 equations to show the propagation step in this reaction. Okay, a free radical substitution mechanism has 3 parts or 3 steps to the reaction. In the first step, you'll have the first step is initiation, followed by propagation, and lastly termination. During initiation, a free radical will form from the reactants. So this reaction has chlorine reacting with ethane to form chloroethane plus HCl. Initiation will form a free radical from the chlorine molecule. The chlorine molecule will dissociate to form 2 chlorine atoms. Now, since chlorine is in group 7, it has 7 electrons in its outermost shell. One of these is going to be unpaired, which makes the chlorine a radical. This is the first step. And during the second step, a chlorine radical will then go on to produce another radical by combining with the ethane molecule. So this will be chlorine radical combines with an ethane molecule to form another radical. It knocks out a hydrogen atom from the ethane, and the chlorine radical will combine with this hydrogen atom, leaving behind an unpaired electron in another radical. Now, this radical resulting from ethane can also then go on to produce other chlorine radicals. The most important thing here is that there must not be more than one radical on each side of the equation. That's the feature of a propagation step, that one radical reacts with a non-radical species to form a stable species and produce a new radical. And during the termination step, two radicals, for example C2H5, and the chlorine radical will react to produce a non-radical species, which is the product of this reaction. Part C, trichloromethane is another halogenoalkane which forms when propanone reacts with sodium chlorate. Sodium chlorate is made from chlorine in a disproportionation reaction. Identify a reagent and conditions that can be used to convert chlorine to sodium chlorate. Well, this reaction in which chlorine reacts with sodium hydroxide to produce sodium chlorate has this equation, and it can be carried out using cold sodium hydroxide. Part 2, define disproportionation reaction. This is a reaction in which the same species is both oxidized and reduced in the same reaction. In this case, that is going to be chlorine. Chlorine in its reactant form has oxidation state of 0. It will then be reduced. The oxidation state of chlorine will be decreased to -1 in sodium chloride, and it will be increased to +1 in sodium chlorate. So as you can see, the oxidation state of chlorine both increases and decreases. In other words, it's both oxidized and reduced in the same reaction. All of these definitions are something that you will need to memorize to be able to score these marks easily. Part 3, write numbers in the boxes to balance the equation showing the reaction of propanone with sodium chlorate. On the reactant side, there is a fixed number of carbon atoms, that's 3, which means there must also be 3 carbon atoms on the product side, which you already have over here. That means we don't need to increase the number of carbon atoms. So these first two products, there must only be one of them in this equation, and then you have 3 plus 3, 6 hydrogen atoms, fixed number of hydrogen atoms on the left hand side. That means you need to have 6 hydrogen atoms on the product side as well. There's 1 hydrogen here, 3 over here, so that's 4 in total. We need 2 more, so that's 2 sodium hydroxide molecules. Okay, now let's see if we can balance sodium, chlorine and oxygen atoms. There is a total of 3 sodium atoms on the right hand side, so we'll need 3 sodium on the reactant side as well, and that also balances out the chlorine and oxygen atoms. Part 4, aqueous silver nitrate dissolved in ethanol reacts with an aqueous solution of trichloromethane. State what's observed in this reaction, explain your answer. So whenever you have silver ions and chlorine ions free to react together, they will undergo a precipitation reaction to form the white precipitate silver chloride. Question 3. The group 14 elements show a change from non-metallic to metallic character down the group. Table 3.1 shows some properties of group 14 elements, carbon and tin in their standard states. The table is incomplete and you are supposed to complete it. Let's start with the electrical conductivity of graphite. Graphite is a good electrical conductor due to the electrons that are free to move between the layers in the structure of graphite. In the structure of graphite, there are only carbon atoms, and each carbon atom is single bonded to 3 other carbon atoms. Now, carbon atom being a group 4 element has 4 electrons in its outermost shell. 3 of the 4 electrons are used for forming these single bonds, and the last one is free to move between layers, which will allow the electrical conductivity. The type of bonding in graphite is covalent, since graphite is a non-metal, and the type of structure in tin is a giant lattice. As you can see, it has good electrical conductivity and metallic bonding. So metallic bonding has the giant lattice type of structure. Part 2, identify the lattice structures shown by graphite. Well, graphite contains only the non-metal carbon atoms. There is no metal, so it can't be ionic or metallic. Therefore, it is a giant molecular structure. Explain why tin has good electrical conductivity. Tin, having metallic properties, will have delocalized electrons in its structure that are free to move throughout the structure between the cations. B. Carbon is found in inorganic compounds such as carbonates. Write an equation for the reaction of magnesium carbonate with dilute hydrochloric acid. So magnesium carbonate reacts with HCl to form magnesium chloride. So that's 2 chlorine atoms as well as water and carbon dioxide. Describe the thermal stability of carbonates down the group. This is a fact you need to memorize as well. It increases. Down the group. For group 2 carbonates, ammonium carbonate undergoes an acid-base reaction with sodium hydroxide. Explain this statement. Let me start by writing the equation for this reaction. You have ammonium carbonate, which will react with sodium hydroxide to produce sodium carbonate. So that's 2 sodium atoms as well as water molecules and ammonia. You have 2 ammonia, 8, 10 hydrogen atoms, 6 are here, so that's 4 over here, right? In our syllabus, we are used to seeing an acid-base reaction. Okay, we are more used to seeing acid-base reactions between common acid and bases like sodium hydroxide with sulfuric acid or hydrochloric acid. The reason those species react as or act as acid is because they donate protons. Now, even though you have a base over here, ammonium ion is a newer base for us to encounter. Ammonium ion, which has dative covalent bonds in its structure, can also dissociate to produce a proton. This proton is the reason the ammonium ion is acidic in nature, and it can undergo acid-base reaction with sodium hydroxide. This proton will be accepted by sodium hydroxide or the hydroxide ions. Since these 2 molecules react to produce water, this is going to be an acid-base reaction. Part C, figure 3.1 shows a sketch of some of the ionization energies of silicon. Part 1, complete the graph in figure 3.1 to show the trend, to show the 3rd to 6th ionization energies of silicon. The values of successive ionization energy. Okay, what is ionization energy? This is the energy required to remove an electron from 1 mole of gaseous atoms. First ionization energy will remove the first electron or the outermost electron of silicon. Second ionization will then remove an electron from a positively charged silicon ion, and so on. The values of successive ionization energies, or these energies for each element, increases because the positive charge on the ion gets larger and larger with each electron removed. So let's say during the first ionization energy, you will have a positive charge on the silicon ion. During the second ionization energy, this will result in a plus plus 2 charge on the silicon ion. The first ionization energy over here is smaller than the second ionization energy, because in the first ionization energy you will remove an electron from a neutral element, from a neutral atom. In the second ionization energy, you need the energy to remove an electron from an already positively charged species, which is going to be much harder due to the stronger force of attraction of the positive charge. So there's going to be a general increase in the successive ionization energies from third to the sixth ionization energy. Sometimes the difference between some successive ionization energies is greater than the others when the number of principal shell changes. For example, the ionization energy that's required to remove an electron from second shell will be much greater than the ionization energy to remove an electron from the third shell. Since the second shell is closer to the nucleus, there is going to be a large difference in the energies required to remove these electrons. Silicon, being a group 4 element, has 4 electrons in its outermost shell. The first 4 electrons, that means the first 4 electrons are removed from the same shell, and the fifth electron will be removed from a shell that's closer to the nucleus. That means there is going to be a large difference between the fourth and fifth ionization energies. In fact, this will be the largest difference that you will see in this graph. So generally speaking, the ionization energies will increase, and the largest difference will be observed between the ionization fourth and fifth ionization energies. So let's say somewhere around here. Construct an equation to represent the second ionization energy of silicon. So you have to remove the second ionization energy, you will start with a silicon that already has a positive charge. And remember, ionization energy equations must always include the gaseous symbol. This will result in a +2 charge in the gaseous ion form, as well as an electron. The figure 3.2 shows the boiling points of simplest hydrides of group 14 elements, carbon to lead. Explain the trend in the boiling points of group 14 hydrides shown in figure 3.2. The boiling point of a compound or a molecule depends on the strength of the attractive forces between the molecules. These are the intermolecular forces, and it does not depend on the strength of bonds within the molecule, which are intramolecular forces. So that means the boiling point depends on the force between two chlorine molecules, which are intermolecular forces, and not on the strength of the carbon hydrogen bond itself, which is the intramolecular force, right? That means going down group 14, the intermolecular forces must change to result in this increase in boiling point. The stronger the intermolecular force between two molecules will be, the higher the boiling point is going to be, because you will need a much higher temperature or much larger amount of energy to break the intermolecular forces. So what's the type of the intermolecular forces between group 14 hydrides? Since these are not ionic compounds or metals, the intermolecular forces will be due to instantaneous dipole and induced dipole forces. And these forces depend on the number of electrons in a molecule. The larger the number of electrons, the stronger the dipole forces will be, the stronger the dispersion forces will be. So going from carbon to lead, the atomic number increases, which means the number of electrons in a hydride molecule will also increase. This will result in an increasing strength of instantaneous dipole-induced dipole forces between the hydride molecules, which is why you will see an increase in the melting point of hydrides down the group. Part 2, deduce the shape of a molecule of silicon hydride. That will be a tetrahedral shape, because the silicon or the central atom has 4 electrons in its outer shell and it is surrounded by 4 hydrogen atoms, all connected by single bonds. E part 1, write an equation for the formation of silicon chloride from its constituent elements. So, you will have silicon reacting with chlorine to form silicon chloride. Since we have 4 chlorine atoms, let us balance that. Part 2, describe what is observed when a small sample of silicon chloride is added to water. Silicon chloride, being a covalent chloride, reacts with water to undergo hydrolysis, and this reaction will produce silicon oxide as well as hydrogen chloride. Now, silicon oxide will form a white precipitate, but because we are using only a small sample of silicon chloride, we won't be able to see that in this reaction. However, you will be able to see misty fumes or effervescence due to HCl. Silicon oxide is a white solid that melts above 1700 degrees Celsius. Silicon chloride is a colorless liquid at room temperature. That means silicon chloride has a much lower melting point compared to silicon oxide. That means the intermolecular forces in silicon chloride must be weaker compared to intermolecular forces of silicon oxide. Explain the difference in melting points of these two compounds with reference to their structure and bonding. Let us look at the structure of silicon oxide first. In this structure, which is a giant covalent structure, each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. And this will result in the production of a giant covalent structure that where all the forces result from the strong covalent bonds between silicon and oxygen that give the silicon dioxide its high melting point, whereas silicon chloride is only has a simple molecular structure where you have the silicon chloride unit, and there are going to be intermolecular forces between two silicon chloride molecules, and these intermolecular forces are much weaker compared to the strong covalent bonds between silicon and oxygen. So, let us start by answering with reference to structure and bonding. Silicon oxide or silicon dioxide has a giant covalent structure, and it derives its strength from strong covalent bonds. On the other hand, silicon chloride has a simple molecular structure. Where the forces or intermolecular forces are not as strong as the covalent bond strength. Therefore, silicon chloride will need much less energy to overcome its intermolecular forces compared to the energy that is required to break strong covalent bonds in silicon dioxide. F. Tin forms an amphoteric oxide. Amphoteric oxides are those which can react with both an acid and alkali to undergo a reaction. Suggest the formula of the tin compound that forms when tin reacts tin oxide with sulfuric acid in an acid-base reaction. So, this reaction will produce a salt as well as water, The salt will use the ions here, the reacting ions here that produce the salt will be the tin as well as the sulfate ions, and the remaining the remaining ions will form a water molecule. Oxidation state of oxygen in a compound is -2. Since there are 2 oxygen atoms in tin oxide, you multiply that by 2, and to that when you add the oxidation state of tin, which is unknown, this should sum up to 0 since this is a neutral compound. That means X, or the oxidation state of tin in this compound, is +4. So if you have tin with its oxidation state of +4 and sulfate ions with their oxidation state of -2, that means you will need 2 sulfate ions to neutralize the charge of 1 tin ion to form a neutral product. So this is the formula of the compound or the salt that will result from this reaction, and additionally you will also have water molecules forming as a result. Since you have 2 sulfate ions, 2 sulfate atoms on the reactant side, you must balance that, and here is the balanced equation to this reaction. Not required to write the entire equation, and just need to write the formula, which is like so. Question 4. Propanone is an important organic reactant. Figure 4.1 shows some of the reactions of propanone and its derivatives. Reaction 1 is a nucleophilic addition reaction. In a nucleophilic addition reaction, a nucleophile will attack the double bond in propanone and result in a product that does not have any double bonds by addition of this nucleophile. Complete figure 4.2 to show the mechanism for the formation of A from propanone include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. So the reactants that we'll use for this reaction are potassium cyanide and hydrogen cyanide, where hydrogen cyanide will dissociate to produce a proton as well as the nucleophile over here. So the nucleophile with its negative charge will attack the carbon atom, the carbonyl carbon that has a partial positive charge, because oxygen is a lot more electronegative, so it will pull the bonding pairs of electrons towards itself, leaving in a negative or partial negative charge on the oxygen. So the lone pair of electrons on the nucleophile will be driven towards the partial positive charge of carbon in the carbonyl functional group, and one of the pairs of electrons in the double bond will then be gained by oxygen in this bond. This will result in a negative charge on the oxygen from an extra electron, and here you will have the partial positive charge on the carbon atom is now neutralized due to the nucleophile. Now the negative charge on the oxygen here will be attracted to the positive proton which had dissociated from the acid earlier, and this will result in the product formation. Part 2. Explain why A does not show optical isomerism. Again, optical isomerism can only occur when the central carbon atom or a carbon atom is single bonded to 4 different atoms or groups of atoms. You have the same 2 groups of atoms on this carbon atom, so it's not going to show optical isomerism. Suggest the reagents and conditions for reaction 2. Reaction 2 is a hydrolysis reaction in which the cyanide or the nitrile group is hydrolyzed to a carboxylic acid group. So here you can use sulfuric acid for carrying out the reaction. C. Reaction 3 is a reduction reaction. Construct an equation to represent reaction 3. Okay, in reaction 3, propanone undergoes reduction to form propan 2-ol. That's going to be CH3COCH3. It reacts with the reducing agent to form CH3, CH, putting the hydroxyl group in brackets because it's a substituent, and CH3. Now here you have 6 hydrogen atoms and there are 2 more hydrogen atoms, so that's how you'll balance this equation. And you're supposed to name this product, which is propan 2-ol. D. State what's observed in reaction 4. Reaction 4 is the reaction between a ketone with 2,4-DNPH. Whenever 2,4-DNPH reacts with an aldehyde or ketone, it will result in an orange precipitate. E. Explain why Felling's reagent does not react with propanone. Felling's reagent is a weak oxidizing agent that's often used as a test for an aldehyde, where this Felling's reagent will react with an aldehyde to produce or oxidize the aldehyde to carboxylic acid, as well as the production of cuprous oxide, which is the red precipitate which indicates the presence of an aldehyde. However, the Felling's reagent is not strong enough to oxidize propanone, so this reaction will not occur. F. Compounds A, B, and C can be distinguished using infrared spectroscopy. Figure 4.3 shows the infrared spectrum of one of the compounds. Okay. The infrared spectrum of each compound will be unique due to the absorptions that are caused by the bonds in the functional groups of that compound. Here, A, B, and C all have a carbon. All of them have a hydroxyl group. Therefore, all of them will have absorptions that are caused by the carbon oxygen bond, as well as the oxygen hydrogen bonds resulting from the hydroxyl group. And this absorption, that means all of A, B, and C will have the, let's see what's the value for, these bonds. It is this one over here, as well as 3200 to 3600. That means all of A, B, and C will have this absorption between 3200 to 3600, which we can see right over here. So this is not going to be indicative of which compound is represented by this infrared spectrum. If we want to determine or find out which of A, B, and C this spectrum is shown, we'll need to look at the other peaks of the spectrum and determine which functional groups are causing the absorption in those particular ranges. Let's look at A. It has got a specific functional group of nitrile, so this will cause the triple bond between carbon nitrogen atoms will result in an absorption between 2200 to 2250 range. B has a unique functional group of carboxylic acid, where you have the carbonyl carbon atom, and this carboxyl functional group will result in a peak between 1670 to 7040 on the spectrum. C only has methyl groups. Now this will result in an absorption between 2850 to 2950. All of these values are used from the table given in this on the same page here. But this range is not going to be unique to compound C only, because A and B, as you can see, also have methyl groups. So they'll also have absorption in the same range. Therefore, in conclusion, the broad peak over here is not conclusive. In addition to that, the range between 2850 to 2950 will also not be the distinguishing factor between A, B, and C. So we'll have to look at other peaks. Since there is no distinguishing factor on C, that means we'll have to look at the functional groups of A and B. Whether we have a peak in this range or this range shown by the spectrum. As you can see, this peak over here, it is very close to, it's just above 2200. That means this peak corresponds to the triple bond between carbon and nitrogen atoms in the nitrile group. Therefore, this spectrum must be of compound A. Explain why the absorptions between this range are not helpful to determine which compounds produces the spectrum. Once again, this will result from carbon-hydrogen bond, which are found in all three of the compounds. So all of them are going to have absorptions in this range. Identify which of compounds A, B, or C produces the spectrum. So that's again A, because the spectrum shows absorption that's unique to the bond, the triple bond between carbon nitrogen atoms in the nitrile group of compound A. And this is it. We are done with this paper. Thank you for watching.